Now what we have is we have this Faraday law. Right? So I'm gonna turn make. Okay, I am going to open my whiteboard. Now what is the Faraday law? What did I talk about that last time? Hello? Hello? And no one answered me and you asked me to record it.
I'm just having trouble in my mic. I keep unmuting it, but it's not. I'm not sure if you can hear me or not.
Oh, I can hear you now, right?
Yeah, I was talking before, but it's not working, so I'm not sure what's wrong.
Now we are talking, this lab 7 is all about the Faraday. Now, what is the Faraday law? Right? Now, Faraday law is really from Michael Faraday. Right? Now, what Michael Faraday think about it? Remember, we have something called the Ampere law. Did your teacher say that? Hello? Hello?
Yeah,
What? I said Ampere law. Your teacher said Ampere law? What the Ampere law said, Ampere law said if you pass a current to a wire, you're going to create the magnetic field right, around the wire. So then what is, if I put it in layman term, what is the Ampere law? Ampere law means the electricity create the magnetism, right? Now that was I think it's around the early of the 19th century, right? Then not very late, not very short after that, right? Faraday law thing, Michael Faraday thing about it, whether we will have magnetism. Create the electricity, right? So in other words, can the magnetic field create the electric field, right? When you have electric field, mean you have the voltage, you have the current, right? Make sense? Hello? Are you there?
Yes.
Yes. Okay, what is another guy? Lisa, are you there?
I'm here.
I'm here. Say something, right? All right, then. So in other words, it's all about this. If you think about it in deep way, it's all about this symmetric, right? So if the electricity can create a magnetism, can it be reversed? Magnetism create a electricity. So therefore, Faraday had this idea. So what he is doing is he have a he have a coil, right? Now this coil connected to a battery. Right. So you can turn on the switch. Right. And then, and the other sense, and the other way of that, you have another coil here. So in other words, I have a primary coil and a secondary coil, right? And this coil connected to a voltmeter. Okay. Now then, the idea of Faraday is when I close the switch, then I will have a current going through, right? Is that right? When the switch is closed, then I will have the current go through the coil, right? Am I right? Now, if your current go through the coil, then you're gonna create the magnetic field, right? The Ampere laws. Well, the question is, I have this appearance of that magnetic field. Are we gonna induce? The question is, the question mark is going to induce current on the second coil. Are you with me? Are you with me? Hello?
Yes, we are here.
Now then the Faraday found out the answer really yes or no. Right? Why yes or no? Yes. Why yes? Now when he just turned on the well, right? When the switch is on it's closed in this particular moment, right? So at the moment, so very short time, right? And what happens? What Faraday see there, right? Faraday see the pointer switch flip. The pointer of the voltmeter flip, right? Good. So mean there's a current go through the secondary coil. But what is the no? Right? No mean what? Right? No mean that once the switch kept closed, the voltmeter, I should say the pointer will not move at all. Right? The pointer of the voltmeter will stay put. Good. Hello. So therefore, the answer is yes or no. Right? And then later on, Faraday thought about that, and then what he's doing is he is modify his original idea. So what happened is right now I am going to have a voltmeter used to detect the current, right, or the voltage, and then connected to a coil. Good. Hello. Are you there?
Yes, I'm here.
Okay. Now, then he modified the experiment. I have a coil, I have a voltmeter, right? But right now, the way we create a magnetic field is not from a coil connected to a battery. The way we create a magnetic field, I'm using a bar magnet. Right, and north and south, right? You know the magnetic field is gonna go up like this, right? We did that last time, right? Now, what he's gonna do that is he's gonna move the magnet in through the coil, right? Magnet penetrate through the coil. So mean the motion is in and out, right? Good. in and out, right? Then what he observed that is, he saw this pointer will going left and right. You got it? Hello? Where the pointer will go left or right. So if the motion faster, then the pointer will flip crazy, right? Will move, flipping back and forth, left and right very fast. So in other words, he got an idea is what? This induced voltage or induced current is really proportional to the speed of the magnet. But the speed of the magnet translated to what? Translated to the magnetic flux. The amount of magnetic flux or the magnetic field line penetrate the coil. You got it? So therefore, depend on time, right? So how fast they are going it depend on time. So therefore, he will have this empirically, right? And then he divide this expression, right? The induced EMF on the coil, or you can write the voltage on the coil, right? It's okay. Should be equal to what? Should be equal to negative the changing of the magnetic flux divided by the time. Or the magnetic field line, right? So depend on the time, right? If you move faster, the time will be shorter, right? Then the induced voltage will be larger. So if your magnet is stronger, then the induced voltage is stronger. Right? Make sense? Now, also depend on the number of the turn, right? So you should have to write, you should put an N here where we should put an N. N stands for number of turns of the coil. Good. So that will be the Faraday law. So what we are doing next week is we want to prove the Faraday law, right? You understand what I'm saying? So what I'm saying, this experiment is simulate the Faraday law induction. Namely, the induced voltage on the coil is depend on the relative motion of the magnet. So by changing to two coil, getting stronger, right? See the light bulb, the luminosity getting stronger. That make sense?
Yes.
I'm changing, right? Changing left and north and south, right? Changing. Okay, that's what we're gonna do, right?